Welcome CHEM200. This is part 2 of chapter 9. You have chapter 9, remember the big one, big homework assignment out there, and then I've posted chapter 10 as well, so that's available. Come see me in office hours. Let's talk about this. There's a lot going on in this chapter, so it'd be great topics that we could talk about. Still have the withdrawal date and quiz 5 coming up. Please note again that ACS study guide, if you're wanting one of those, you need to order it. Okay, so chapter 9 finishing, and then we get on to chapter 10, and quiz 5 is out there as I mentioned. So we're going to finish up this chapter 9. I want to start with a constant pressure calorimetry problem, and then we're going to go into some new topics, and you can see it's all about enthalpy. So Hess's law, that's delta H. Bond energy, that's delta H. This is the enthalpy of a reaction from bond energy. This is the enthalpy of formation, and this is the lattice, the enthalpy of lattice. So all of this is delta H on this part. So calorimetry, constant pressure, that was the Q equals MC delta T, but definitely these problems were a step up from Chem 152. So I want to point out a couple of things here. You've got a reaction, that's sulfuric acid with potassium hydroxide, and you have a temperature change, 20, and the temperature rises. So what does that tell you? Right away, that should be a red flag. If the temperature is rising, it tells us something about this reaction. And the question is asking for calculate delta H in kilojoules per mole of sulfuric acid. Some things you'll need are the density and the specific heat capacity of the solution. So go ahead and go for this. Constant pressure calorimetry, that's Q equals MC delta T and Q equals negative Q, and go from there. So a couple things I want to point out is the enthalpy of the reaction. That's the Q of the reaction. That's what we're looking for. And remember, the Q equals the opposite Q. So the heat of the solution is the MC delta T part. So that's the mass, specific heat capacity, delta T. So the mass of solution, there are two 25 mil reactants put together, so that's a total of 50 mils. Density gives us a total of 50 gram solution. And the C, we're using, assuming it's like water, and delta T was given to us. Please note the delta T in Celsius, 6.67, is the same thing as in Kelvin. Okay, but you do not get C and then add 273 to that to get Kelvin. Okay, so remember this is a delta T. You can add 273 to this and add 273 to this and then subtract them. It's going to be this 6.67. However, you definitely know if you add 273 to this, it does not equal 6.67. So now that's the mass, the C, and the delta T. So that gives the Q of the reaction. Okay, but look, that's in kilojoules. Remember the problem was asking for kilojoules per mole, so you take the volume of the sulfuric acid, the molarity of the sulfuric acid, and that gets you moles of sulfuric acid. So now you can get kilojoules over moles of sulfuric acid, and that gets you negative 112 kilojoules per mole. Remember I said red flag, the temperature was rising. That should be because it's exothermic. That negative number there tells us it should definitely be going up. So now we're going to talk about enthalpy of reactions. Okay, so we've already said the sign is a really big thing. That tells us about the direction. So that was endothermic, exothermic. Well, now if we change the direction, the sign's going to change. Okay, magnitude tells us about amount. So we already saw in stoichiometry, if you had 1 mole of it, it gave you 1 delta H. But what if you changed it to 4 moles? Well, that gives you a different delta H. So let's take a look at that. Hydrogen's a reactant, fluorine's a reactant, and you get 2HF. So we get this number. We can see that it's negative. That's exothermic. We can see that it's 1 mole. 1 mole gives us 2 moles. So those are all important things to notice when you have a thermochemical equation. So let's take a look. Well, what if we reverse it? Now HF is the reactant, hydrogen's the product, fluorine's the product. If we switch the equation, flip it, we change the sign. Okay, if this is exothermic, then the same thing has got to be endothermic. same amount as well, magnitude. So that's changing the sign, so the direction makes a big difference here. What if we change the amounts? So instead of having 2 HFs, we have 1 HF. We have half of this, so you can imagine then you're going to have half the heat. So the enthalpy, the sign stays the same as up here, but it's half the value of that one because we have half as much. So go ahead and take a look here. What is the enthalpy change associated with the formation of 3.40 moles of HF? So right away we look and say, well, that's HF, that's the formation. So how are we going to get to this to get to our number? So go for it. And multiple choice here, you can see this is very common in chapter 9. Same answers given, but opposite signs. You have to know your sign. In this case, formation, that's going to be a negative number because we know that's going to be exothermic. And if we have 3.40 moles, okay, we have 3.40 moles of HF, then we need to multiply that by the stoichiometry. So this equation has 1 mole of HF, and it's, you know, common because we're used to going to mole ratios. Well, what am I going to? What's the moles of that we need? You don't use moles here, you use this. So that's your numerator, minus 273. And you do this calculation, and you can see the number's going to be negative. It's going to be bigger than this, so you can cancel out positive. Positive, didn't have to do any math, but if you do the math, you can see it's negative 928. So that's looking at the enthalpy of a reaction. Now, this is actually one of my favorite areas, Hess's law. Okay, what we're going to do is look at a combination of reactions and treat them like puzzle pieces in my mind and sum it up to solve for unknown enthalpy. Okay, so what this means, you're looking for the enthalpy of an overall reaction that maybe you can't actually study in the lab. Maybe it's unknown, but you have, remember state function? You have some steps that if you add all these steps up, it leads to the overall reaction. What you can see then is it's just additive. You add these steps up together, their enthalpies added equals the overall enthalpy. Okay, what does this look like? Stepwise process, and we're going to use this at the end of this chapter for a big, complicated stepwise process. And so if we look here and we say, well, we need A plus 2B to go to 2D. Well, we don't actually, can't do that reaction. For whatever reason, that can't happen. But I know A plus 2B can go to C, and then I know the reaction of C to go to 2D. So, state function, if you take these, so take this arrow and this arrow, you can see you can solve for the value of going from A plus 2B to 2D. So this is the summation of Hess's law, putting these things into action. I think symbols sometimes a little more confusing, so let's do actual example of this. Okay. So determine delta H for the following reaction. So this is what you're going for. Okay, this is what you want. And these are your puzzle pieces down here. Okay, and they're enthalpies. So my approach to this is to start out left to right. Okay, so on the left is 2NOCl. None of these have NOCl on the left, but I know this is on the right. Okay, so I'm going to take that reaction and I'm going to flip it. And I get NOCl, switch it over here to NO, to this half chlorine. Okay, so what happened earlier when we switched a chemical reaction? If we switch a chemical reaction, that means we've got to flip the sign. So I flipped the sign now, 38.6 kilojoules. Wait a minute, I'm not quite done here because remember, I need 2 NOCl. Okay, so if I change this by adding a 2 here, I have to add a 2 to everything else, change a 2 here, and if I change a 2 here, that takes me down to 1 chlorine. Oh yeah, if I change the chemical equation with a number, I've got to change that value with a number. Okay, so now that's 2 times 38.6. That gives me this chemical equation. All right, so then next, if I go to the right, I need nitrogen by itself. And I can see over here's nitrogen, but it's on the reactant side. Oh, look, I also need oxygen, and there's oxygen here on the reactant side. So I also need to flip this reaction. Okay, so if I flip that one, then I go NO, and that's half nitrogen and half oxygen. And you'll see these fractions in chapter 9, and I'll show you even more reason why that's the case here later. So we flipped it, so that then changes this to negative. So we're keeping track of the chemical equation and the delta H value. Okay, but let's double check here. NO really isn't our focus. Remember, our focus is nitrogen, oxygen. So I'm going to multiply this by 2 as well, because I need 1 total, so that's this by 2. This by 2 cancels out. This by 2. So that cancels, we get 1 nitrogen and 1 oxygen. And of course, we've got to multiply this by 2. Okay, so let's put it all together. 2 NOCl, that's what we wanted up here. Excellent. Check, I got it. So that looks good. Wait a minute, I got 2 NO here. How does that help me? Because it's not in the following. Double check though, you've got 2 NO on the right of the arrow, you got 2 NO on the left of the arrow. That cancels. Okay, then you can see there's 1 chlorine over here. Got that one, check. There's 1 nitrogen, 1 oxygen. So these are all the things that we're looking for. So our balanced chemical equation down here is the same as that. So then our delta H of this reaction is the sum of these. 2 times 38.6 plus 2 times negative 90.3, and that gets us to our answer, negative 103.4. And as I mentioned before, if you have chapter 9, same sign, same answer, different sign, B, A, so those are detractors. All right, go for it. What is the enthalpy change for this reaction? Again, this is complicated here, going through these steps, but I'd go left to right. So this one, you keep written as is, NO's on the left, okay? A single oxygen atom is on the left, okay? Well, we have this one, so we didn't do anything up here. This one stays the same. Here, we need to flip it, get the oxygen on the left, and we need to do it by 1/2. So that's a negative 1/2 delta H3. So then we'll have the oxygen, we'll have the NO. Okay, we have the NO2 here because it was in the first one. So we've got our NO2. We just now need to make sure everything else cancels. And if you look, this would be stayed as is. The ozone needs to be flipped to cancel this. O3 is ozone, so this has got to be canceled. So we flip this one, and now our ozones would cancel, because that'd be on the opposite side. And this is 3/2 or 1.5 O2 on the left. And remember, this was flipped and 1.5 O2s, so that would also cancel. So now we have 1 times delta H, negative delta H2, negative 1/2 delta H3, and you should come up with negative 304. So this is Hess's law. You'll continue to use Hess's law in Chem 201. I think it's really fun. You can definitely see how you got to take pieces and then put them together to get the overall. So the next piece really is going to cover some chemistry that goes into previous material. Okay, what I mean by that is we need to know the bonds of molecules in order to calculate the bond energies. Okay, so that's review of previous material, but now you can see how it comes in with delta H. Okay, so if we're thinking about this, FF is a bond, HH is a bond, so these are molecules, they're made up of bonds, and that tells us about the energy associated with the bonds that have got to break. Okay, so if they're reactants, the bonds have got to break, and if it's products, the bonds have got to form. So what we're seeing here is this is exothermic, negative 546, so we actually have a lot of bond energy here in the product. So that's what an exothermic tells us, more bond energy in the product, and endothermic, more bond energy in the reactant. So this takes more energy to break these bonds. That's why overall it's endo. So the big takeaway, reactants, we always take energy, endothermic, to break up reactants. Okay? Exothermic, we always release energy when products are formed. So how you determine if it's negative exothermic for the reaction or positive endothermic for the reaction is the bond energy of products. That's greater, that's exothermic. Product or reactant energy, bond energy is greater, that's endothermic. So double check here, which of the following must be true for the following reaction? So think about the bonds. Well, if you look here, this is a bond, fluorine to fluorine, but these are single fluorine atoms, okay? So to break the bond, remember, to break FF to be two single atoms, that takes energy. That's delta H is positive, and that's endothermic. So bond energy is what we're going to be focusing on and talking about. So the definition of that is it's that the energy required to break 1 mole of bond in the gas phase. And it just said, emphasized, that's endothermic. If you're breaking bonds, that is a positive delta H, that is endothermic. And we've seen this before. Bond energy, remember, single, double, triple bonds are not created the same. They have different lengths and they have different bond energies. So triple bond has higher bond energy than the single bond here. And these are all carbon-carbon. Well, you could look and see if they're different atoms, hydrogen-hydrogen. You can see it has a different bond energy than hydrogen-carbon. So you can imagine now where we're going. You drew all of these molecules and thinking about what do molecules look like, what bonds are there, even what orbitals were overlapping, all of that, to now we can see and calculate the enthalpy of a reaction based on what bonds are being broken and what bonds are being formed. So this is a Hess's law problem, okay? So remember Hess's law, we want to know the purple. Well, how does it go from here to here? Well, the way you can do it, you can break off this piece, you can break off this piece, do a stepwise, that's this step, and then you go down here, you add this piece together, and add this piece together. Personally, the way I do this is break everything, okay? So CH4 plus chlorine, I would break every CH bond and break the Cl bonds and then form all new bonds, okay? So what I mean by that is you're breaking 4 CHs and you separate it all into atoms, and I'll show you how to do this in the next one, and then you form 3 new CHs. So that was 4 of these we're breaking, and we're forming 3 of these, and we're forming 1 CCl and 1 HCl. So I would keep track of everything that's broken and everything that's made. Okay, so let's take a look at that. Remember, bonds broken, the reactant, that's endothermic. So you sum up everything that's broken. So that's what I would do, just sum everything up and then subtract everything that's formed, because that's a negative for the products, because those are exothermic when you form the product. Exothermic, we already looked at this. Weak bonds break, strong bonds form. And endothermic, that's the weak bonds forming, strong bonds are breaking, so it takes a lot more energy overall than it makes it endothermic. Okay, so what does this take then? It takes good previous chemistry. Those are good Lewis structures from before, and it takes the data table in your books to look up these values, and I encourage you to do that. So this is chapter 9. Look up your data, and you can see that slide before here. This is table 9.3. So if you look through this, you basically just have to keep track of what bonds do I have and make a list. So in this case, you'd be provided with the values, and then you can look up and see what you've got. So I'll tell you the values here. Carbon, hydrogen, that's 414 kilojoules per mole. And then oxygen, it depends on if it's a double bond or single bond. Oxygen double bond is 498. Okay, so then we go over here. Carbon oxygen double bond for carbon dioxide is a little bit different. That's 799. So that's 799 for both of these. I'll go back here and make a note on this 498. And carbon hydrogen said was 414. So we need one other value, and that's this OH. And if you take a look here, it's got to be careful with stoichiometry. Okay, so the OH is 464 kilojoules per mole, but you've got 2 of them. So wait a minute, that's 1, 2 per water molecule, but you have 2 water molecules, so that's 4 of this. That's 799, but wait a minute, you got 2 of those. Okay, and over here we've got 1 oxygen molecule, but you've got 2 of those. And you've got 414, but you got 1, 2, 3, you got 4 of those. So you've got to keep track of your bonds and the amounts. And then lastly, remember endothermic is positive, making bonds is negative. So those are negative 4 times 464, negative 2 times 799. Put those together, then you get the overall estimate of the delta H for the reaction. So that's negative 802 kilojoules. So we're going to continue with enthalpy, and now we're getting to a really important part, and this is a key word here. This is going to really focus on a definition, and that's formation. Okay, so this is the standard heat of formation, or the enthalpy of formation, and what we're seeing is the change associated with the formation reaction for a substance. Okay, what does it mean to form a substance? It's got a very specific definition. It's the pure compound that's being formed. And if we take a look here, it's the change in enthalpy when 1 mole is formed. That's the definition. 1 mole is formed, and it's formed from its elements in their standard states. So what does that mean? Well, oxygen's an element, O2, and its standard state is a gas. Okay, so then an enthalpy of formation would not start from oxygen in the liquid form. Okay, that would be not a standard state. So what we're looking for then is these elements, their standard states. Please note the elements have a delta HF of 0, and that's going to come in important when we're doing some calculations. So standard states, we want to emphasize that. If it's a gas, that means it has an actual pressure of 1 atmosphere. Okay. If it's a liquid or solid, it's the most stable form, okay, of the element, and the temperature can vary. Actually, this isn't standard temperature and pressure STP. This is standard state, but usually we look at this at 25 degrees Celsius. If it's a solution, it's got to be 1 molar. So these are all the standard states. All right, so formation equation. Definition, we're forming 1 mole from the elements in their standard states. Okay, so we've already seen this one, HF gas, that's the compound. This is the element, fluorine gas. This is the element, hydrogen gas. And take a look, if we're forming 1 mole of this, that's the definition. Remember, 1 mole, that's why we have these fractions now. So that's half hydrogen, half fluorine. That gets us to this 1 mole of product. So that's the delta HF. So you see the subscript, that's the delta HF, or the formation, because it's 1 mole of a compound from the elements in their standard states. Okay, so now you go for it. What is the formation reaction for aluminum chloride? What I encourage you to look at here is first, if it's not 1 mole, get rid of it. Okay, then we go over to the left side of there and say it should be elements in their standard state. Aluminum's a metal. It is not a gas in its standard state. Okay, we can see here this one was already crossed off because of the products. And if we see here, chlorine is a diatomic. So that's wrong. That means we're left with the aluminum, and look at this, fractions, even more. 3/2 of chlorine get you to aluminum chloride. All right, now you go for it. Calcium carbonate, hydrogen sulfide, and ammonia. So we gotta know what these substances are. That's nomenclature. Formula for calcium carbonate. What's the formula for hydrogen sulfide? What's the formula for ammonia? And then go for it. Write it from the elements, 1 mole of product. You can see here, start from the right. If you've got 1 mole, then that's calcium's an element, carbon's an element, oxygen's an element. Calcium's a metal, that means its standard state's solid. Carbon's a non-metal, it can vary, but for carbon it's a solid. And then oxygen's a gas, and we have to account for the fraction to get us to 1 mole of the product. Hydrogen sulfide, H2S, hydrogen diatomic, that gets us to H2S. Ammonia is NH3, that comes from the elements nitrogen and hydrogen, and then use the fractions to get us to 1 mole of product. So what we're seeing is that these enthalpy of formations, or these delta HF values, are in the back of your book, and you can look them up for lots of different substances. Okay, so there's more and more pages of this, of substances that you can look up, and they're giving you values in kilojoules per mole. So what does this mean? How are we going to use this? Okay, Hess's law. Told you, it's great. Okay, so remember, Hess's law is, well, we want to go straight from this substance, methane and oxygen, that's our reactants, to this one, carbon dioxide and water. Well, what you can actually do is say, well, we don't know how methane and oxygen is going to get to there, but we know that we can do the decomposition. So that's opposite of the enthalpy of formation. So now we're in the elements. So we take it back to the elements, and then we can form the compounds stepwise. Form carbon dioxide and form water from the elements. Okay, so this is what's happening with Hess's law. So what I want to emphasize here is this equation to do this looks very similar to the bond energy. Okay, so I want you to take a look at your textbook. This is page 395. It gives you the equation how to calculate the delta H of the reaction. And it looks so similar. I really want you to look at this and see the difference. So in this case, what we're doing is we're taking the delta H of the reaction, and we're doing this by summing up. Wait a minute, that sounds familiar, summing up. But in this case, we're summing up starting with the products. Okay, so this is the coefficient of the products, and we're multiplying it by the enthalpy of formation of all of the elements. Okay, so that's for the products. And then we subtract the reactants. So this is products minus reactants. That is the opposite of what we saw for the bond energy. So it's really easy to get these confused. So I'm trying to put it detailed here. Products minus reactants. Okay. Remember how bond energy, we said reactants are positive, products are negative, and we just add them together. So now I'm going to be a little more specific here. So remember, we're starting with the products. So the products are 4 CO2. So these values are in the back of the book for your homework, or they'd be given on a quiz or exam. So I'd go 4 times CO2, and it's got to be the same state. So that's minus 393.5 is the gas. And these are additive. So then I'm adding the liquid water, and count that I have 6 of them. So the liquid water is down here. So that's 6 of these. Okay, so this is my product side. And then this is where you need the big negative, products minus reactants. And take a look here, okay? So we've got this ethanol, great, so that's right here. That's no problem. That's minus 2 times that number. And then take a look at oxygen. What do you notice? It's not on this list. The reason, remember, this is an element. It's in its standard state. Its standard state has a value of 0 then. So that's it. We've finished setting it up. Products minus reactants. Don't include the elements in their standard states. And of course, I keep telling you, this is how the multiple choice are going to be. Do you know your sign? Are you doing products minus reactants? Are you doing reactants minus products? So here, really emphasizing, this is products minus reactants. That's negative 2,734. So we're covering a lot of delta H here, and we've got one big thing to cover left, okay? And so that is lattice energy. Again, Hess's law, it's coming in. But what we need to know first is that lattice energy is the energy associated with forming the crystalline lattice, cations and anions, from the gaseous ions. What does this mean? Gas ion plus gas ion equals a solid, and then just look at this glowing. Okay, that should tell you this is exothermic. Heat is emitted. Okay, so delta H of lattice is exothermic because the ions in the gas phase all come together to form the solid. So what I really want to draw attention to here is all the different types of reactions that we're seeing in this chapter. We just saw enthalpy of formation. The formation was the element in their standard states forming 1 mole of compound. Here we can see the ions forming 1 mole of the ionic compound. So what we're going to do is see Hess's law, big hypothetical series of steps representing the formation of an ionic compound from its elements. Okay, so if we take a look, this is a lot going on here. What I want to point out is this are the elements, and that is the ionic compound. So that small purple thing is the enthalpy of formation. So what we're doing is taking the, again, the state function route stepwise all the way around it, coming back and solving for this. So what are the steps? Okay, so let's take a look here. Okay, first the step is sodium solid to sodium gas. Wait a minute, how do we go from a solid to a gas? That's sublimation. Okay, so that's solid to a gas. Next step, we go from a molecule, Cl2, to an individual chlorine atom. That's bond energy. Okay, so that's bond energy. This is the enthalpy of sublimation. And look at this, sodium gas, you know this one, to sodium ion. What was the definition of a metal in the gas phase going to an ion in the gas phase? That's ionization energy. Okay, that's endothermic. So you can see we're gaining energy here as we look up the axis here. We're going up in energy. Then take a look, we're on the downside now. Chlorine to gaining an electron, that was electron affinity. And this last one, okay, gas phase ions, Na plus gas, chloride gas, to the solid, that's our new definition of lattice. Okay, so review, previous chemistry, ionization energy, electron affinity, sublimation, this chapter, chapter 9, bond energy, lattice energy, and enthalpy of formation. So lots of examples of chemical reactions here in lattice. So the example here I've written is how do we put all this together? Okay, and so I've included this slide for you and the answers to be able to walk through stepwise to see what happens. It's Hess's law, remember? Okay, so look at this. Give the information below, determine the lattice energy of magnesium chloride. So remember that everything is going to end up equaling the enthalpy of formation. So that's our final answer, is enthalpy of formation. Okay, so if we take a look here, that means we need some magnesium solid on the left. Oh, guess what? We got it right here. Excellent. Okay, now look at this. Magnesium gas on the right cancels magnesium gas on the left. And if we keep going with this, we can see that we're going to get to this following enthalpy of formation. So let's take a look. 1/2 chlorine. Okay, well, we don't need 1/2 chlorine. We need a full chlorine. So if we multiply this by 2, that means we have to multiply the delta H by 2. Okay, so now that takes us to 1 chlorine. So we got 1 chlorine and we've got 1 magnesium. And then if we go down here, if we said, well, if you got 2 chlorines up here, we got to have 2 chlorines down here. So if we multiply that by 2, we got to multiply this by 2. Okay, so we saw the ionization energy, magnesium plus, magnesium plus. The second ionization energy gets us to magnesium 2+. And if we multiply this, there's 2 electrons. Cancel that with 2 electrons. So we're missing one thing. Okay, and what we're missing is something to cancel, Mg2+. So that's Mg2+ gas phase. And we're also missing something. Here we canceled the chlorine, we canceled the chlorine. We need to cancel the chloride in the gas phase. And remember, we multiplied that by 2, so there's 2 chlorides. And you can take a look then, we still need this magnesium chloride, the solid. That's how we put all this together. Okay, so every step is added. And we had all of these, and we named them all or in the previous slide. But the really ones that stand out, that's the enthalpy of lattice, and that's what is being asked for. Okay, so if we have now our Hess's law plan all laid out, we can adjust for it. Say we need the enthalpy of the lattice. All of these add up to the enthalpy of formation. So we can put it in now, enthalpy of formation. It doesn't matter, it's so long and complicated. We adjusted this and this. That's all that we changed. Here, and the key, remember, lattice should be a negative value. So there's a lot going on here. So I encourage you, come to office hours to talk about this, because this is very difficult to walk through. The good news is we're going to end on a few slides of conceptual of lattice energy. So what those are is showing that the lattice energy depends on the size of the ion. So remember sizes. Lithium, very small, and it goes increases in size as you go down. So the smaller the size, the greater the lattice energy. Okay, so the magnitude. So that's negative 834, large magnitude, small size. The biggest on the list, cesium chloride, see, the biggest distance between them, and the smallest lattice energy. And it also depends on the charge. Okay, so size, which means distance between the charges, and then what are the actual magnitude of charges. So you can see calcium +2, oxygen -2, massive difference between magnitude of calcium oxide and sodium fluoride. So with these two key things, then you can address this problem. So put these in order based on the magnitude of lattice energy. So I would encourage you, first think about charges. So +2, -2, +2, -2, that is going to be more exothermic, so greater negative for lattice. And then these are your +1, -1, +1, -1. Then look at magnesium and strontium and compare the size. And if you see, remember the smallest has the biggest, and then the next one. And then again, these are the same charge, but lithium smaller. That's why it's bigger than sodium bromide. So this concludes the big chapter, chapter 9. Come see me if you want to talk about these topics.